in the interest of making sure we get both presenters an adequate amount of time, I hope you've held your questions. I have about 6 or 7 questions that came up from that. I hope you have some as well, and we'll return to those after the next presentation. The next presentation is from Steve Bitar of ExxonMobil. Steve is program manager for a program that you may be familiar with. I don't know if you can call it a breakthrough program or whatever you can call it, but Steve is going to talk today about why we should care about open and bring his perspective to that. So Steve Bitar, ExxonMobil.
Thank you, Harry. Okay, so I was flying out here the other day, Monday, and I thought to myself, last year when I was here, no one talked about collaboration and sharing. And I'm going to open up my talk talking about collaboration and sharing. And I put some notes together. And of course, all you heard about this morning was the theme of collaboration and sharing. So I thought I was so clever. Nonetheless, let me give you my spin, what I want to say about it. So open is more than open interfaces between applications. It's also open interfaces between people, open interfaces between enterprises. Or maybe I should say it should be or it could be. It's really the belief in the holistic theme that the whole is greater than the sum of the parts. Now, when I thought a little bit about our industry, and I apologize if maybe I'm not familiar enough to know our entire history of automation, I was really struggling to come up with any real broad industry activities that really demonstrated collaboration in a really broad effort. A lot of little micro activities taking place. But I struggled, other than safety, process safety, I thought we did a pretty good job. And the other area is sharing, and I mean specifically sharing of intellectual property. You may know about 2011, Facebook started the Open Compute Project. And Facebook basically said, look, we're going to take everything that we know about data center design and we're going to put it out in the public domain. And they didn't do this because they were being altruistic. They just said, look, this isn't really a source of competitive advantage for us. And when I tie up resources working on this, I could have had them doing something else. So they gave everything away. And I thought that was quite clever, right? First, a little odd, but soon Google joined, eBay joined, Bank of America joined. I mean, I think they have like 16 companies. Wonderful example of sharing of intellectual property where, counter to your intuitive belief, sometimes it's better for an enterprise to share some things, not everything. So in the spirit of collaboration and sharing, I've changed the presentation up a little bit to try to include some things that I used internally, or we used in our team for open process automation in ExxonMobil to try to convince our management that this was a very good idea. You know, like all organizations, we have a very lengthy release of technical information process, so it took a little time to get these things out. But nonetheless, it's not everything I would like to say, but it's a step in the right direction towards a little more openness and communication. All right, so let's get going with that background. This is just a reminder of the things that you heard this morning. So Don was pointing out that we're trying to reduce lifecycle costs, which of course also includes the cost of wholesale replacement, a significant component. But also increase value generation, and to Christian's point as well. You know, in the case of refineries, it's not just throughput, it's the value of your product, it's low-cost feedstocks, well as, you know, lowering your fixed and variable operating expenses. This is the vision that we just keep putting up again and again to remind everyone where we'd like to end up. One thing we did change between this year and last year is we were saying low-cost integration of best-in-class components, and someone pointed out, well, maybe we don't want best-in-class components. Maybe we want fit-for-purpose components because, I don't know, it's a bakery and we're only, you know, we're going to run for 5 or 10 years. I don't want to overpay. Leading-edge capability and performance, you know, just think of Moore's Law. We want to preserve our IP software. We want to stop having to do the equivalent of rewriting all of our PowerPoints and Excel files every time the IT organization brings your new laptop to you. Wholesale replacement projects we talked about. Adaptable intrinsic security. Keep emphasizing the adaptability of security. So you don't want to be left with a system that's not secure and you have to wait 30 or 40 years to add a layer of protection, especially if we get into this more open world with a lot more open flow of information in and out of the system. And scalability. And then, in an odd font, I'm not sure where that came from, we want to make this point. We have some constraints and boundary conditions. This has to be applicable to brownfield and greenfield facilities. We want it to be commercially available on the open market, and we want to use publicly available industry standards. Excuse me. All right, so I have two slides. One to talk a little bit about the importance of industry standards, and the other one, something that ties directly into the Nomura activity and what Christian described earlier. I'm going to present a little, some places where we have parallel thinking and some counterpoint as well. But this is really related to standards. So we were taking a look at kind of the evolution of information technology, and some of you here, maybe most of you, remember this, this era with the mainframe. For the younger folks in the room, think server, and then this sort of local dumb terminal, think thin client in today's technology, where you hit the keyboard, you type a letter, it goes off to the mainframe, it echoes it back, and eventually shows up on your screen, and you can imagine how fun that was to program things in that era. So what happens? So the PC market comes along, and now you have this local autonomy and speed, and you don't have to wait, for your applications to run. You don't have to share time. So that was sort of the end of the mainframe era. But then again, networking technology starts to emerge, and there's this argument that, well, maybe everything doesn't have to be done on my local little laptop. Maybe I can, economy of scale, I can put some things on a data center and execute them there. And eventually, we move up to this architecture we see today in the IT world, which is you have this vertical and horizontal partitioning of function, and you partition however it makes sense, running things in the cloud, running them on a local server, running them on an edge device, which going to be a multitude of edge devices. And they sort of come full circle, starting on the cloud, so to speak, and working your way right back up again. Well, that's a nice end model, and it has this horizontal partitioning of function that really is enabled by the introduction of standards. You need standards to enable that innovation, and that's what we see in IT. So what can we learn from this? We put together the same slide for operations technology, and we said, okay, what did it look like way back in the day when we started basic regulatory control? You probably can't see that, but that's a little Foxborough pneumatic controller that does proportional integral control. It has a sensor and an actuator. Admittedly, I probably didn't put pneumatic devices there. I made a mistake, I think. But what you got out of that was what you call single loop integrity or modularity. So if that device broke, you lost one control loop. You also had economic scalability, meaning you want to add one more device, one more controller, you just add one more. It's double the cost, triple the cost. It's kind of linear in scaling. And you also had interoperability as well. And okay, that's a bit of a stretch, right? It's a 3 to 15 PSI signal, so you could cascade two of these devices together as long as both subscribe to that standard, interoperable standard of 3 to 15 PSI. So what happens next? Someone has a clever idea of saying, hey, why don't we take all these controllers and move them up into a central control room, because then I can have better situational awareness, I'll have more stable plant operation, I can tune my loops, I can see what's going on, get the big picture, make more money, push more throughput, lower my costs. But it's a single loop design, still stayed intact. Then comes along sort of the 70s where we introduced this concept of digitizing or digital control of all these loops. We started putting multiple loops into a single controller. Price we paid is we went to these proprietary architectures, and that's where we lost those characteristics that we so dearly cared about, or at least appreciated in the day. So the question is, shouldn't we be returning to an architecture that's quite similar to where IT has gone? And in a way, this is sort of the OPA vision, that we like to see both a horizontal and vertical partitioning of function. But in order to enable that, same exact problem. We need to set the interoperability standards that enable the innovation to take place. Those products aren't going to appear on their own. You have to be motivated, and you have to get around the interoperability problem. All right, so maybe a really simplistic example of the importance of standards. But nonetheless, let me go on to my next slide, which I don't have a good segue for this, other than I put this in here because I knew Christian was talking today, and I've seen the Nomura model, and I wanted to point out what I think is an interesting way to look at the differences between the ideas of where OPA is trying to truly go all the way down to the control system for the open interoperability and modular design, and Nomura is accepting sort of the DCS as a sealed appliance that can be proprietary and closed. So did I advance this too far? Yeah. Let me draw your attention on the left-hand side. So there are these perceptions, right? First of all, the folks on the OPA team, they say, look, You go to open interfaces and you're going to get marketplace competition, you're going to get innovation. That's going to happen. It's a belief. I can't prove it right now. If you talk to other folks, they'll say, wait a second, hang on. Proprietary interfaces are the only way to ensure reliable and deterministic performance. It's the only way to get it. It is, maybe proprietary is the price you pay, but that's what you have to do to get these characteristics. Maybe true, maybe not. That's one of the purposes and objectives of the program, is to establish whether or not we can build reliable systems that are truly open. So if you look at this kind of a grouping of functions inside a control system, what I did is I said, we said, look, back in maybe 20 years ago, what's in the blue line comprised the DCS. So you had the control, the advanced control went into like a supervisory control node, the IO, the HMI, the alarm management, and the historian, and all that stuff was in the package. But as time went on, people wanted choice. They wanted to introduce other components. They wanted to mix and match best in class or best in breed. And that DCS got a little bit smaller. And I'd say now that's probably where we are right now. And this is the drawing that Christian showed up before, where he said, look, you basically have this little, as Don Bartusiak likes to call it, a little triplet of functionality. And Johan Nye as well points out these are the three critical functions. We have to ensure that these things operate and play nicely together. These are the things that keep our plant stable and reliable and safe and secure. And the question we're asking is, can we break up these three components? It really comes down to that simple question. Can we break it up and still ensure the reliability and determinism that we have today? Does opening up those interfaces imply that we no longer have the same availability of our system? Quite important in the process industries, chemical, oil and gas, even pharmaceuticals, pulp and paper, mining. Everyone cares about that question. So our assertion is that this could be done, but it's not as simple as just doing it. First, of course, you need the standards, we talked about it, but you need other ways of testing and verifying that you are going to have repeatable deterministic performance. And there are technologies available to do this. We're looking to the aerospace industry because they connect together hundreds and hundreds of devices in a single avionics platform, and they can verify before the aircraft takes off the ground with the first test pilot, they're going to play nicely together, and you're going to have those safety of flight concerns addressed. All right, so it could be a question of technology. It's a question of risk management, and we think we're ready in this stage in both the IT and OT technologies to take that step. Okay, so I threw that in. I know it seems a little, doesn't quite flow from the last slide to this one, and I wanted to then stop on these 2 points and say, okay, I want to show you the slides, kind of the internal slides that we've been using that I've just recently got some approval to release. And there are really 4 of them I want to go through. And these are the ones that sort of helped us inside of ExxonMobil think, well, okay, maybe there is something to this. Because as you would imagine, you get the management saying to us, sounds great, guys, but is this technology for technology's sake, to Christian's point? Or is this really going to do something that affect the determiners of profitability in the plants that I work in? Is this really going to add value to my bottom line? So my favorite slide, I couldn't find a way to get it through the release process, but I'll figure out a way to do that. But at least you'll see these 4. So this one is directly related to something Christian was talking about. So if you think about hierarchies and sensors, think about a sensor. When you decide you want to provision a new sensor in your plant, what is the first thing you ask? All right? You say, well, what do I intend to use this sensor for? All right, what's its purpose? And from that, you will specify a quality of measurement. So that means the repeatability of the device, the reproducibility of the device, what kind of environment am I going to put it in? Does it need to be class 1, div 2? Does it have to be explosion proof? You spec out your instrument and you buy it. Then the next thing you ask is, what's my quality of service requirement? I mean network quality of service. Do I need that thing for regulation and control? What do I need it for? And that will decide your entry point into the stack. That's how we do it today with this ISA 95 model. So, for example, if I decide I want a sensor for alarming and control, I'm going to plug it right into the DCS. Unfortunately, that is the most expensive way to bring a measurement into the control system, but nonetheless, you get something out of it. You get reliability and determinism, and it will always be there, and you'll have that measurement available to make decisions, automated decisions. There is another footnote I want to mention here, too. If you do truly have a hierarchy between your level 1 controller and your sensor, once you run out of slots on your I/O brick, if you truly have a hierarchy, to add the extra sensor means you have to buy another controller. And of course, that controller has to be redundant, and it needs a footprint and power supply and complexity. So you have this non-linear effect where that extra sensor has to bear the burden of a future capital investment. You make a pre-investment. I know we're seeing a shift in industry now towards the separation of the two, so you can independently add sensors as well as level 1 controllers. But we still have some systems that are being designed with a hierarchical model, which are fine. It's a nice sealed appliance. You lose the network, it carries on running. But of course, you have this, nothing comes for free, and that's the price you pay. All right, so you might bring in a sensor in because you might say, well, look, I just want to use it for alerting and notifications. And quite frankly, I don't care if I lose it once a month. It's okay. I can put that thing up on my MES layer on level 3. If the operator loses it, no problem. But of course, when you push that signal back down again, now you have to really, probably the reliability is, maybe the integrity of the data are there, maybe not. Reliability, because now you're looking at, the ubiquitous Windows platform and Dell boxes and whatever else you use. And if I could back up a step too, if you do put it down in that process control, you put it down on the DCS, the sensor, you might have this choke point problem too. So those devices on the DCS, they could be 30, 40 years old, as they are in some of our facilities today at ExxonMobil, and they only serve the data up at whatever rate they can, and that's not going to improve. You may want more data quicker, but you just can't have it. It could be an endpoint constraint, it could be a networking constraint. All right, so you got a learning notification. Suppose you say, look, I just want to bring it in for analytics. All right, so I can bring this thing up to my business LAN. I can put a wireless signal up there. I'll just put it into a big data analytics, big data lake. I'll do my analysis on it, and I'll come up with really clever relationships. The problem with all of these decisions is that reprovisioning is a problem. If you decide later that that sensor you brought in for data analytics would actually be very useful for the operator to use for decision making or for a process control loop, you have to reprovision it. You have to go wire it back into the system or bring it in wirelessly into the DCS to get the availability and the integrity that you need. So what we're really proposing is this flatter architecture. If you just think about it from the perspective of sensors, we like to see a flatter architecture that treats the sensors in a more democratic fashion. And Don's point, Don always, he likes to remind everyone we're not talking about a single network here. This is a segmented network. It says nothing about the topology. We do understand the importance of the availability of the design, but it's just an abstract drawing. We're decoupling the sensor from the consumer. The data producer, data consumer are independent in this architecture. But why do we care about that? Well, you bring the sensor in for monitoring, data analytics, and you decide later I want to use it for control. It's a configurable change in the quality of service. You can reprioritize it dynamically. You don't have to reprovision. We believe that it will lower the cost of sensor integration rather than being forced to pay the premium every time you want to bring it in the most expensive way. And of course, you have the bandwidth problem solved too. You're going to design this thing to be able to support the bandwidth. And there are some DCSs being designed with these flatter architectures as well. I don't want to say this is completely novel though. Good innovation happening. Okay, that's number one. Number two, if you think back about those single loop pneumatic controllers that we were taking a look at before, and they had one input, one output, one sensor and one actuator, and they did a simple thing like control a flow, a pressure, a temperature, or a level. Now the amazing thing is, you fast forward to today, and I have this box that virtualizes those level 1 controllers, those old single loop controllers. I can do anything that I want. I can put any calculation I want in for regulation and control, and guess what I do? I build a virtual single loop emulation of an electronic or pneumatic controller. For some reason, our heads can't get out of this idea of one single input, one single output pairing for regulation and control. We're not forced to, yet we elect to. There are better ways to solve this problem. Here's an example. In fact, let me go back. I have a simple process heater on the left-hand side. So this is a process fluid that's going through a fired heater. I'm assuming there are two flows. We'll call them passes, say, of some cold liquid coming in, you heat up. There's an outlet temperature on the outside. There's fuel gas coming into burners. On the bottom of the drawing, you're heating this material up. You're trying to control it to an outlet temperature. You have an O2 analyzer on the stack to make sure you don't put yourself in a substoichiometric condition, which would risk a possibility of explosion. So how does this thing work? This matrix tells you how things interact with one another in this process. So you have on the left-hand side things you manipulate or move to control it. You have the fuel gas flow. You have the stack damper, which affects the air flow rate through the burner, so you always have enough air. You don't cause an explosion. You have the individual pass flows. And along the top, we call that a coil outlet temperature because the process piping runs in a coil through the furnace. You want to control the temperature, you want to control the O2, you want to control the box pressure, which we call draft, and the differential temperature between the passes for optimization, and maybe they're bridge wall temperatures because you don't want to burn off all the refractory inside the furnace. Everything here interacts with everything else. But here's how we solve this problem. We pair up coil outlet temperature with fuel gas, we pair up O2 with the stack damper, and we forget about the fact that everything interacts with everything else. And the question that we asked ourselves is, why don't we solve this problem differently? Well, part of the problem today is you just don't have the compute power. Now, if you buy a state-of-the-art DCS, some of them will come today with the compute power to solve that problem simultaneously. You can buy commercial off-the-shelf solutions. You can. Of course, you have a DCS that has another 20 years left in it. Forget it. You're going to have to wait 20 years. Or if it has 30 years, you're going to have to wait 30 years. But this is a paradigm that we just can't quite get our heads around, that why are we still solving problems if we only have single-loop electronic or pneumatic controllers? Why do we have a one-to-one pairing when we have multivariable interaction between inputs and outputs? Why can't we improve the stability and performance of our plants by using different control algorithms that are admittedly far more intensive in terms of compute resources? Okay, so that was number 2. This is the third one. So I am, the last guy in the world you want to ask, security questions to. It's not my thing, right? Not my area, but I'm quite curious about it. I always hear this phrase, security through obscurity. Now, I apologize if maybe you're a million miles away ahead of me on this one. But okay, so first let's start with the definition. So this is just your standard knowledge base of all knowledge in the world. Wikipedia is saying that it's the reliance on secrecy of the design. And it says that even if you have vulnerabilities, the designers believe that if the flaws are not known, it'll be sufficient to prevent a successful attack. So I would say, well, okay, what's wrong with that? What's wrong with having obscurity being a level of security? I mean, what is wrong? You have to figure out how it works, so it is a layer of protection. So our discipline technology lead for security said, Steve, you need to get online and read about Kirchhoff's principle. And I know, who? And he said, Kirchhoff's principle, read up about this guy. But Dennis is quite clever. Rather than trying to convince me of something, he wants me to go figure it out for myself. So I start reading up and I find this little quote here, and it says, hey, a crypto system should be secure even if everything known about the system is known about the system except the key. Except the key. And what's really amazing about that quote, when I dug in a little more, is that quote was made in 1883. Kirchhoff was a Dutch cryptographer, and he had like 7 principles he listed. I just grabbed one of them. And if you think, and if you look at the NIST guide to General Server Security, published in 2008 and updated in 2011, they're saying the exact same thing. So I would say this principle has truly passed the test of time. There's something to this. So I had to think about it a little bit more, and I said, my punchline is this, that, yeah, sure, obscurity is a layer of defense. It sure is. But arguably, it's neither strong nor is it lasting. All right? If you listen to what he's saying the Kirchhoff principle applies to when you design the system. Right? You need to design it assuming they already know how it works. And what they don't know is the key, and whatever that key may be, whether that's an encryption key through some key management system or maybe some other blockchain technology or whatever is out there on the horizon, I don't know. But the penny, the drop in my mind was that the value of that principle is only realized before the system is designed. And here we're talking about building systems up from scratch again. This is our opportunity to integrate Kirchhoff's principle into design and make sure that we follow this principle so that we don't fall into that trap of believing that a secret is really a long-lasting defense. Loose lips sink ships. Okay, that was 3. I have one more. So this slide we've batted around internally, and that's always been a little bit contentious, but you'll kind of get the gist of this whole thing after I get through it. The idea is that you have these information systems, right? You have your level 4 and above, and then you have level 3 to level 1 below, and that's the operations technology layer. And you have this flow of state information going up from the information system, right? The state of the plant, the pressure, the temperature, the flow, what feed am I running, what products am I making, who's on shift, and what are my lab results, et cetera. And what you'd like to see are some transactional services being made available to the OT layer, right, coming back down from services. Now, I can tell you that in ExxonMobil and quite a few of the critical process industries, there's not much of that happening today. And let me show you why. Or let me show you what I mean by that. Maybe that's the first step. So the problem is there's no trust between these domains. And that's probably for good reason. You don't want the virus going up, you don't want a virus going down. Both have very significant consequences, right, in either direction. So there's no trust. So we have very limited flow of information back and forth. But why do we care? So you have a console operator, it's 2, 3 o'clock in the morning making critical multi-million-dollar decisions. And what is wrong with the idea that everything known about a particular asset that's causing a problem is available at their disposal? Why shouldn't all the information known about an asset in the field be available to that process operator? Maybe not even within the enterprise. Maybe everything known in the globe about that particular asset is made available. So I have to credit ABB for putting this thought into my head a few years back. There's a brochure you guys can find online where they talk about their aspect object technology. They're talking about a particular way to do this, but they were very clever in seeing the need for it. So in this case, what might happen? So you see something going on with a pump. You right-click on the pump. You get a bunch of things that would tell you everything you need to know about that particular pump. You go to the very first one. You click live video feed. It's Bob. It's Bob out there mucking with the pump again. Nothing to worry about. He's always out there tinkering with something. So, or maybe it's not Bob. Maybe you really want to look at the work order history of that pump and find out what's been going on. So you go to the bottom and click on work order system. You look at the work order history. Maybe you say, look, I want to generate a work order. It's a smart device out in the field. It interrogates it, brings back information, fills out your work order, fills your name out, everything except the priority. Click, you submit it, you send it in. But there are other things too. Diagnostics from the individual device, think heart communication to smart devices. You have troubleshooting guides, standard operating procedures. Data sheets. I don't know if an operator would need data sheets, but are there spare parts in the warehouse? What about phone a friend? You got the remote operation support center on the other side of the world. They're up and waiting and they're ready to go. And the asset owner for that particular class of equipment picks up the phone and says, what's going on? So I guess I'll close on this slide by saying, when I ask our security guys, okay, look, if we have intrinsic security embedded all the way down in the edge device itself, is that going to enable us to do these kind of clever things? And the answer is no, not necessarily. So I think what I can say is that with the security model today, with our sort of bolted on approach and without that intrinsic security built right down into the microprocessor, without anything like that, secure by design concepts, you're definitely not going to do that. But there's a shot if we do this right, we'll be able to convince ourselves that open flow of information will be possible. But the first step is enabling security, because that's the business opportunity we're trying to address. Make sure the critical decision maker has everything he or she needs at any point in time to make a decision and not have to wait for the rotating equipment engineer to come in on Monday morning before asking the question, which may be too late. Okay. Enough of that. My last slide. So I stole that sentence from Don. Don likes to say there's an industrial renaissance going on, and I think he's right. We just need to think differently about the way we do things, break these historic paradigms, some of the things that we talked about earlier. Not everyone cares about building clever applications that extract more value out of your plant or improve your yield. Sometimes you have a simple process and you just want it to run really well. But whether you're focused on adding value, whether you're just trying to lower your cost, you're in a commodity business, or maybe you just care about security, right? There's something in this program that will appeal to everyone with those sorts of interests. I want to remind everyone, of course, for the users specifically, that yeah, you can let this decision go, and you can put in a proprietary system, and don't worry, that train will come back to the station in 20, 30, or 40 years. So get involved now, right? So you at least have the option, right, to move in a different direction. And I guess the last point talking about security is, it very may, it's just an assertion that it may be that in order to compete in future, tomorrow's economy, maybe you need the more open flow of information in and out of your system. Maybe you can't afford to have the local services in the plant to do the things you do today. Maybe you have to buy those services, and to do that, you need the flow of information. You need secure connections to be able to do that. So finally, we want to encourage everyone to join us on this journey. So you can join the open group. Don this morning pointed out all the open group folks. You can talk to them today if you're interested. Join the forum. There are many forums you can join in the open group. This is the one we're interested in. We want you to send us your best and your brightest. That's all we ask. So I want to thank you for your time.